Hi, this is Dr. Mohammed Hamami, and this video is about finding minimal cost circulation in a flow network. And also it describes what's called the out of kilter algorithm to solve this type of problems. I selected this problem among many other network flow problems for many reasons. First, many optimization problems in network flow can be converted to finding a minimal cost circulation. Moreover, the method used in this algorithm are applied to other algorithms. And so going through this algorithm and the sub functions of this algorithm will help in addressing other problems like the max flow problem, some transportation problem, and so forth. The second, it links to my previous video about linear programming, and it uses the duality theorem of linear programming in deriving this specific algorithm to these specific problems. And the third, the proof of convergence is not complicated, but it requires to go over many network scenarios. So in this video, I try to simplify this and make it easy to remember. And the fourth is this video provides an Excel visualization of the many steps of this algorithm, and also it enables the viewers to understand better how the algorithm works, and of course on how to program it. Now there are two books that I strongly recommend among many other books on the same subject, and of course about linear programming. The first one is called Flows in Networks, and it's the author are Ford and Fulkerson. These two mathematicians are the one that derived this type of algorithm. For example, the out of kilter algorithm is often referred to as the Fulkerson algorithm. And it is the book is of theoretical nature. It lists many problems in network flow and then derived specific algorithm for this type of problems, and it goes through the proof of convergence. However, this book doesn't have examples or problems to solve, so it's just a theoretical book, but it is an excellent book. And the second book is about linear programming in general by Professor Shvatal, and it has chapters on this topic. Professor Shvatal was a visiting professor at Stanford University, and I took graph theory class from him. And I also taught this class at UCLA. So most of the material in this video are from a previous class notes. So now let's move on to formulating what the problem is, and then deriving the algorithm, and then going through the proof of convergence, and finally going through the Excel visualization of the algorithm. Nodes labeled from 1 to 14, and then it has 29 arcs. Okay, and on each arc, for example, this one, 2 to 7, there is 3 numbers that are an input to this problem. There is a lower bound on the flow, and an upper bound on the flow, and the unit cost. So the objective of this problem is to find the optimal feasible circulation. So this optimal solution, first of all, it has to be a circulation, which means that any flow coming into a node must equal to the flow going out. So in this case, I only have one arc, so the flow on this arc, and I have 2 outgoing arcs, so the flow on this arc must equal to the sum of these 2. And second, the flow must satisfy the lower bound and the upper bound. So if I have, let's say 5 is in between 4 and 10. So, and then it also has a unit cost. So if my flow is 5, the cost will be 5 times 3, which is 15. And so the Kilter algorithm will find, if an optimal solution exists, it's going to find a feasible circulation, and it is the feasible circulation that has the lowest cost among all feasible circulations. So now let's formulate the minimal cost circulation problem. So we have a set of node n, finite set, and then we have a set of arc from the set C. So this is a directed arc from x to y. And then F will denote the flow on that arc. The UB denote the maximum flow on that arc, and LB denote the minimum flow. And C is the unit cost on that arc. And to simplify notation from now on, we're gonna do this notation. Like if we have two subsets of n, then F of u comma v is just the flow between u and v. So it's the sum of x belonging to u, y belonging to v of f of xy. So instead of carrying this sum, we'll just write it as f of u comma v. Now the optimization problem now is we're going to minimize the cost. So on each arc, the cost is unit cost times the flow, and we sum that over all the arc in C. Now the constraints on this flow, first of all, it's called the conservation flow. At every node, the flow coming into x is equal to the flow going out of x. Okay, so f of nx minus f of xn equal to 0. So this f here is a sum, like this notation we did here. And the other set of equation, we have the flow is between the lower bound and the upper bound. And of course, f is greater or equal to 0. So this is the minimal cost circulation problem. So first of all, it's a linear programming problem, right? This function is linear, these constraints are linear, and so are these constraints. Everything is linear. And therefore, we can, theoretically, we can use the simplex algorithm to solve this problem. But this problem has a special structure. The A matrix, if you're going to form the A matrix, you're going to find that it's mostly zeros in that matrix. Only it's the coefficients of that matrix are either 1, -1, and 1 here. So, and it's a sparse matrix. There's not an arc for every x and y. There are just some limited number of arcs. So here, therefore, we're going to need some special algorithm to solve this. All right. So now, before we develop the algorithm, we're going to find what is the dual of this linear programming problem. So I refer you to my previous videos on duality and stuff like that. And here we're going to have a variable for each constraint. So this is equal to 0. So we're going to have for each node. So for each node, we're going to have a number a variable associated with it, and it's going to be unrestricted because this is equality. And then we're going to have a gamma of xy corresponding to this inequality right here. And then this inequality will change it to minus f greater or equal to ub of xy. So therefore, we're going to attach a variable theta, which is greater or equal to 0 for this constraint, okay? And then just we read the every constraint in the dual is a column in this matrix here. So to recap, we have a beta of x. This is a variable for each node, and we have theta of xy for each arc, and a gamma of xy for each arc. So the gamma corresponds to the LB, the theta corresponds to the UB constraint. So here we read the objective. So we read the right side of the primal, and that gives us maximize for all the arc in C of LB of xy times gamma of xy minus UB of xy times theta of xy. Remember, we changed the constraint f greater or equal to b to minus f greater or equal to UB. So that's why this -1 is coming from. And then we read the column of the matrix A in the primal. We get gamma of xy
corresponding to the LB constraint, minus theta of xy minus beta of x plus beta of y, which here I put it on the right side. Okay, and this number here comes up. For each xy arc is going to appear here with the coefficient of -1, and it's going to appear in the y constraint corresponding to the y node. And the y node is going to have x here and y here. So it's going to appear of a coefficient 1. So that's why you have beta x minus beta y. Okay. And then, of course, we have gamma greater or equal to 0, theta greater or equal to 0, and the beta number are unrestricted. So this is the dual. Now, the reason I put beta x and beta y on this side, it's because if we let a of xy equal to c of xy plus beta x minus beta y on this right-hand side here. So this is called, from now on, it's called the adjusted unit cost. So it's the unit cost adjusted by beta x minus beta y. So if you want to maximize this, we could do the following. We could fix beta and maximize of the gamma and theta. And then whatever we found, we'll optimize that with respect to the beta variables. And we're going to do that. So if I fix beta, so the right-hand side is fixed, and I maximize only on gamma and theta, this becomes a separable program. Every this variable gamma xy and theta xy appear only in one term. So maximize the sum is going to be the sum of the maximums. So, and then it becomes, each one becomes a simple two-dimensional problem. So you got maximize ax minus by subject to x minus y less or equal to this number a. And that's easy to find the optimal solution. The optimal solution is gamma to xy is equal to the max of 0 and a, and theta of xy is the max of 0 minus a. So when a is positive, gamma xy is equal to a, and theta is equal to 0. And when a is negative, gamma of xy is 0, and theta xy is equal to minus a of xy. And then we replace this value in the objective function, and if we get rid of these constraints, so it becomes maximize over beta over all the arc of LB of y times the gamma, which is maximum, this maximum, minus UB of xy times this maximum. So this is the dual problem, and the dual here doesn't have any constraints. The beta could be anything, and we want to maximize over beta. Okay. Now that we have the primal and we have the dual, we could use, from my previous video, we could use what's called the complementary slackness theorem. And the complementary slackness theorem says the following. If f and beta are optimal, if and only if a of xy bigger than 0, then gamma is greater than 0. And remember, gamma corresponds to the inequality f greater or equal to the lower bound. So when the dual variable is strictly positive, that inequality is an equality. So f of xy is equal to the lower bound. Same thing with axy negative implies theta is strictly positive, and f is equal to the upper bound. And then when a is 0, then f is just between the two. So this is the necessary and sufficient condition for any circulation and a set of dual numbers to be both of them optimal. Okay, and we're going to use this. This is the basis of this out of kilter algorithm. So now, given a circulation f and a node number beta, okay, and then each arc we calculate is adjusted unit cost a, cxy plus beta x plus beta y, and f is the flow. Then, so this is circulation is not necessarily feasible. So this arc is going to be in one of 9 possible states, and I group them into 3 categories: optimality, infeasibility, and other. So optimality is like the complementary slackness theorem says. If a positive, f is equal to b. A negative, F is equal to UB, and then A equal to 0, the flow is between the lower bound and the upper bound. So there's three possible states for optimality, okay? And in that case, we're going to define the Kilter number. And for these three states, we're going to say the Kilter number is 0 by definition. Then comes these four states, which are infeasibility. So A bigger than 0, F is less than LB, so it's outside the interval, all right? And here we define the Kilter number to be LB minus F. So this is the amount of infeasibility we have on that particular arc. A negative and F bigger than UB so it's outside the normal, the lower bound, upper bound. So the degree of infeasibility is F minus UB. A equal to 0, we got two cases, F bigger than UB and F less than UB. So for F bigger than UB, we'll do F minus UB, the degree of infeasibility, and here is LB minus F. Okay. And we have two other ones. So if you look to A positive, F is equal to LB. A positive, F is less than LB. And so we need A positive and F bigger than LB. And the same thing here. A negative, we need F less than UB. So these are two states. And the Kilter number is defined differently. Why? Because if an arc is in this state, F bigger than LB does not mean F is infeasible for that arc. All right? F could be less or equal to B and bigger than LB. So in this state, we do measure, because A greater than 0, the optimality is LB. So we do measure F minus LB. That's the condition of optimality. And also in this arc, we could decrease A to 0. If we decrease A to 0 and F is between UB and LB, then the Kilter number is 0. So that's okay. Right. So this measures two things. One is non-optimality, and the other one is to decrease the Kilter number. And same thing with A negative and F less or equal to UB. So it's going to be minus A times UB minus F. So notice that here, first of all, the arc that obey the optimality condition, their Kilter number is all zeros. And this one are all bigger than 0, the other states. The Kilter number is bigger than 0. So now the question is, since we have some arcs in these conditions, we want to bring them to these conditions for optimality. So we have to either change F, the flow, or change beta. So this table shows us when can I change the flow F without increasing the Kilter number. So we want to do the change of flow so that no arc Kilter number increases, and it's either stay the same or decreases. Well, let's look at this, for example, an arc in this state. Well, if F plus means I increase the flow on that arc, and F minus is I decrease the flow. So can I increase the flow on this arc? F bigger than UB. No. F bigger than UB, I jump to this state, which is strictly positive. So I increase the Kilter number. So this is a no. And also, I cannot decrease the flow on that arc neither. Same thing with this one. I cannot increase the flow there, and I cannot decrease the flow on that arc. Now this condition, A equal to 0 and F is between LB and UB. So here it depends. Let's say F is strictly less than UB. All right. Then I could increase the flow up to UB. So the maximum increase would be UB minus F. And also, if F is strictly bigger than LB, I could also decrease the flow all the way to LB. So the maximum decrease will be F minus LB. So this two column shows the maximum of changes you can do to the flow on this arc, specific arc. Now this one here, A bigger than LB, A bigger than 0 and F less than LB. So I could increase the flow up to LB, and I should stop there because that Kilter number is 0. I cannot go beyond that. So here, the maximum increase on that arc is LB minus F. And then here, A negative and F bigger than LB, UB, I can decrease the flow all the way to UB. So the maximum decrease is F minus UB. Equal to 0 is the same way. I can decrease the flow up to UB, but I could go further than that. Since A equal to 0, I can be anywhere between LB and UB. So I could decrease it to UB, and then I continue all the way to LB. So the maximum decrease of this flow is F minus LB. And the same thing with A equal to 0 and F less than LB. I could increase the flow. I won't stop at LB. I can go all the way to the upper bound. So it's UB minus F. And finally, this 2 here, I cannot increase the flow. I will make it worse, right? Increase the flow makes this Kilter number increases, so I cannot do that. But I could decrease the flow all the way to LB, so that's F minus the lower bound. And this is the same thing. A negative and F less than UB. So I could increase the flow all the way to UB, all right? And it's UB minus F. So what this table shows you is, given any arc in any one of these conditions, it gives you whether you can or you cannot change the flow, and by how much, the maximum change you can do. Okay, so to summarize this table here, we're gonna state what the rules are for changing the flow. So if you look to, for example, A negative, F is less than UB, and the change, we can increase the flow to UB minus F, and A equal to 0, and F is less than LB, and if it is less, which is less than UB, so it's going to be the same thing as this. So we can increase the flow all the way to UB minus F. So if A is less or equal to 0, then we can increase the flow up to UB minus F. And if F is positive, if A is positive and F is less than LB, then we can increase the flow up to LB minus F, the maximum. And the same thing with the other case, with decreasing the flow. So here we have some rules, right? We are in the middle of the algorithm, and we have some arc that are out of kilter. That means that their Kilter number is not 0. And so the rule is, if A is less or equal to 0 and F is less than UB, then I can change the flow on that arc. I can increase the flow on that arc up to UB minus F, okay? By UB minus F, not up to, by UB minus F. So therefore, the flow will be equal to UB, upper bound. And same thing with if A is positive and F is less than LB, I can increase the flow up to LB. So the maximum increase is LB minus F. And it's the decreased flow rule is like a mirror image of this. So A less or equal to 0, A is greater or equal to 0. F less than UB, F is bigger than LB, and the maximum is here UB minus F. This is F minus LB. And A positive becomes A negative, and F bigger than UB, and the maximum is F minus UB. You can go back to the previous matrix and do that. So let me go back to here. So I want to emphasize this point. If I have an arc in Kilter means the Kilter number is 0. Look to the flow change. Okay, flow change, we only change it if F is strictly less than UB or F greater than UB. So we will still stay between LB and UB given this maximum. So therefore, and these two, we don't change the flow. So an arc in a Kilter would stay in Kilter throughout the algorithm. Okay, that's important. And also, for example, here, if I increase the flow on this arc by epsilon, okay, so that will reduce the Kilter number. And the same thing with decreasing the flow. Any change in the flow will decrease the Kilter number. So to summarize, an out of kilter arc, that means k is not 0, both flow changes, I mean the increased flow or the decreased flow, will decrease the Kilter number of that specific arc. And in Kilter arc, both flow changes will not change the Kilter number. It will stay 0, which is important. So these are the rules, and I would say the limitation on how much flow changes we can do. So now let's give the overall flow chart of the out of kilter algorithm. So we enter the algorithm by providing an initial circulation, not necessarily a feasible circulation, and a set of dual variable beta values. Okay. So any f, any beta. So we could start with f equal to 0. The 0 everywhere is certainly a circulation, and beta could be anything. Okay. So we enter here and we say, okay, are all arcs in the network in Kilter? That means every arc Kilter number is 0. Yes. We stop, and f and beta are optimal. That's the exit. And if there are arcs not in Kilter, then we go here and we select any arc, x, y, that is out of Kilter. And what we do first is we go to this flow change process, okay, in the network. And the purpose of this is to decrease the Kilter number of this arc with the rules that we already established, okay? And we're gonna see later how do we do that. But for now, it's just a flow change process. We start to change the flow, and it's an iterative process. Iteration after iteration, you change. You may not be able to change the flow all the way to that maximum, but we could do it in many iterations. And if that flow change process was able to make the Kilter number of xy equal to 0, then we go here, update the circulation and the Kilter number, and we go back here. Okay. If no arc are out of Kilter, then we stop. Otherwise, we select another arc xy. And remember, when an arc is in Kilter, it will always stay in Kilter. So this select arc out of Kilter is a finite set. It's not an infinite set where we can choose from. So we select the next one and we do the flow change and so forth and so forth. So we do this loop here many times. Now here's the special thing about the out of Kilter algorithm. We're going to assume that all our input is integer. Okay, like the lower bound, the upper bound, and the unit cost, the initial circulation, and the initial beta. All these are integer. So then the flow changes are all integers. Okay, and therefore the Kilter number stay integers. So throughout the algorithm, they stay integers. And I showed in the previous slide that any flow changes will decrease the Kilter number. One of the Kilter number has decreased, at least one, by at least 1 unit. So you got to find a set of numbers. They cannot increase, and at each iteration, you're decreasing one of them. So this flow process cannot go on forever, right? At some point, when we do this, like this, at some point, there are no flow changes possible in the network. So we have still an arc xy out of Kilter, and I went in, it was unsuccessful, and k was not equal to 0. So then we go here. Then we keep now the flow fixed, and we change the beta. So we go through this node number change process. And this is not an algorithm. This is just one step to change the node number. So when we change the node numbers, keeping the Kilter numbers, not increasing, and even some of them decreasing, then that might have opened some other path for the flow process to be able to change the flow. So if it's successful here, we update the beta, we update the Kilter number, and we go back to the flow change process. And of course, we cannot change the flow because we run out of the flow changes. There are a finite number of those. So we come back here, and then we come back here, and we change the flow number, it's successful. And therefore, we're going to be doing this many, many times. And we're going to show that this node number process is finite. We cannot do that. We cannot change the node number an infinite number of time when there is no flow changes. That's impossible. So at some point, we're going to exit here at the stop, and then with no feasible, and that's the answer to that one will be there are no feasible circulation in the network. So two outcomes, F and beta optimal, and the primal problem is infeasible. So, and this is based on the fact that all our operations that we do here in the flow change and the node change are of integer type. So if our input data is not a rational number, so if you use an irrational number, then this flow change process is not finite. Okay, you may have to have infinite number of iterations, like you're changing the flow by infinitesimal number, and this one is it could take an infinite number of time. And there is an example in Professor Shvatal's book on linear programming that gives that case that this flow change takes forever. Okay, so it's important to know that the out of Kilter algorithm works only with rational data, okay, not irrational data like square root or e or pi or something like that in our in the input data. Okay, so this is the algorithm. Now we have to develop this flow change process and the node number change process. So we have in our flow chart an arc x star y star with out of Kilter, of course, k is not 0. And we want to change the flow so that k, we want to decrease k all the way to 0. So it becomes in Kilter. And one way of doing that is to change the flow on this arc here. So based on the state from our matrix that we did, we have either decreased the flow or increased the flow. So let's do the decreased flow. So to decrease the flow from x star to y star, we need to find a path from x star all the way to y star where we increase the flow. So we take this flow out of here and put it on this path here. So here we're going to have a loop, okay, and we're going to add delta here, subtract delta here. So the flow conservation of flow at this node is valid, all right? And the same thing here. This delta goes on this delta, and the conservation of flow is valid. And we also allow reverse arc, right, in this path here from x star to y star. Reverse because if I add delta here, I can subtract it from here. So the flow conservation is okay. And then from here also I subtracted delta from this. I'm going to add it here. So everywhere here you see we have not changed by making a change in the flow in this epsilon change on this cycle. We're not violating the constraint that F is a circulation. Okay, so now and of course our matrix earlier gives us by how much, what's the maximum decrease we can do, right? Delta. So it's going to depend on these arcs too. For example, this arc is going to have a maximum increase. So we have to compare this to this and take the minimum. So we have to take the minimum all the way down here and this one. And then if that's positive, then we're going to subtract delta from this arc, add it here, subtract it from here, and add it here, and so on. How do we find this path like this? Well, one brute force is to enumerate all of them. Okay. We only have a finite set of arc. Yeah, we should be able to enumerate all the paths from x star to y star, excluding this arc x star y star. And then I go check with the flow with the flow change rule. Can I increase the flow here? Can I increase the flow, etc., etc., and then do that. But there is a method called the labeling process, which is a more I would say better method than enumerating all the paths. So how they does it is we're going to start at x star, and we color this x star red nodes. That's how we start this. And then from x star we look all the arc where x star is one of the it's the origin of the destination. And using, for example, here this is one of them. I check the flow change rules, and this is a forward arc. Can I increase the flow? Well, if it's yes, then I color this, the new node here, I call it red. And also I keep track that this node was colored red from this node. Now we have two nodes that are color red. So we're going to look at all the arcs between the red nodes and the white nodes, and see also using the flow change rules which arc can I change the flow, and I color those red, and so on and so on. At each iteration, I check whether this y star is red or not. If it's red, then we just go backward, which this y star was labeled red from this node, and this node was labeled red from this node, etc., till we reach x star. And now we have a path. All right, we have a path here, and we do the changes that I talked about. So that's what the labeling process is that I'm going to describe formally in the next slide. Now, how about if we have a decreased flow? If we have an increased flow? I mean, the table told us that we need to increase the flow in order to reduce K. Well, then we're going to start from here, from y star. And we're not going to, for example, this one will be plus delta. So we need to find a flow from y star to x star going this way. So we have clockwise loop. All right. And we do the same thing and the same procedure. We check every arc if we can change the flow and so forth. And then we do the same coloring of the node, etc. And once we find the path, then we change the flow accordingly. So the arc going clockwise will increase the flow by delta, and the arc going counterclockwise, for example, like this one, then we subtract delta. So the two cases are very similar. It just depends. Where you start. Here in the decreased flow, we start at x star. In the increased case, we start at y star. Okay. Now, so let's describe formally the labeling procedure that will enable us to find those loops, those cycles. So we enter here with an arc x star, y star, and from the table it tells us decrease the flow by this much, maximum of this. If I could decrease the flow by this much, my arc becomes in kilter. Okay. So let's try to decrease the flow. So we're going to start labeling the nodes, like we color them red. Here we create labels for initially label of x star is two element to it. Now -1 because it wasn't labeled from any previous node, and delta of x star will be that maximum. Okay. And now we have x, big X is the set of labeled nodes or the set of red nodes, and x bar is the complement of it, the set of nodes that are not labeled yet. And then we start the labeling iteration. Now I take a labeled node or a red node and a y that's not labeled yet, and we have an arc xy, forward arc. Here we're going to have to increase the flow. Remember, forward arc, we increase the flow. And the table tells me that I could increase the flow by as much as delta xy, not 0. If it's 0, just we go to the next arc. And then if it's not 0, then I'm going to label y by two things. One is, okay, I label this from x, right? And it's plus because it's a forward arc. It reminds us this is a forward arc. And then I have to do the minimum of this delta theta x and delta of xy. Okay, and then now y is labeled, so it becomes a red node. And also, we look also to forward arcs. That is an arc yx, where the destination is labeled and the origin is not. And here we have to decrease the flow. So, and the table tells us that I could decrease it by as much as delta yx, which is not 0. If it's 0, then we don't consider this arc. Now here I could label y now. I labeled it from x, and it's a minus, reminding us that this is a reverse arc. And we do the minimum of delta of theta x and delta y of x. And we keep doing this. And at every iteration we ask, were we able to label the node y star? Is the y star colored red? If it is, then we stop right there. And we update the flow and the Kilter number. So we're going to change the flow by theta of y star, okay, and that might not be equal to this. So we were able to reduce the flow or make this arc in Kilter. If it's less than this number delta x star y star, then we're going to find another path. All right, we start over, okay, and then we find a path between x star and y star, and we repeat the procedure many times until either the arc x star y star is in Kilter, or I cannot. I'm stuck. I cannot label any more nodes. I have a set of x labeled node and a set x bar on non-labeled node, and I cannot label any more nodes. And here we go in and then we say the flow change process failed, and we exit the labeling process. And then in the algorithm we go to the node change, where we change the dual variables. Okay, so that's the formal definition of the labeling process, of finding out those paths, those loops, the cycles, where we could change the flow. Now when the flow change process failed, I mean, we failed to, so we have an x star y star, an out of Kilter arc, and we changed it as much as we could, but we didn't reach the we weren't able to put this in Kilter. So there is no more changes of flow. Okay, so we exit with an x, the red nodes, and x bar, the white nodes, the labeled node and the unlabeled node. So what does this mean? Here I have an x in x and y in x bar, and I could not increase the flow from x to y. That means that if you look to the labeling rules, it means that if axy is less or equal to 0, then f of xy must have been greater or equal to the upper bound. And if a of xy is positive, then f is greater or equal to the lower bound, and vice versa. Now the reverse arcs, x in x, y in x bar, and here we have an arc yx. If yx is greater or equal to, so the opposite of this, yx greater or equal to, is going to imply that the flow from y to x is less or equal to the lower bound, and a of yx, opposite of this, negative, implies f of yx less or equal to the upper bound. So this is just telling us that we could not label y from x because of the flow change rules. Okay. So in this case, we're going to form two sets. Okay. The first set is the arc going from x to x bar, for which A, the adjusted unit cost is strictly positive, and the flow is less or equal to the upper bound. And the second set is the reverse arc, yx, for which A of yx is negative and f of yx greater or equal to the lower bound. Okay. Now, if A1 is not empty, then I form this what I call delta 1, is the minimum of these A's. Okay. And of course, delta 1 will be strictly positive. And here, we also, if it's not empty, we form delta 2, which is the minimum of minus y over x. So delta 2 is also strictly positive. And then finally, we take the delta to be the minimum of delta 1, delta 2. Now, if A1 is empty and A2 is empty, then we stop. The problem is infeasible. We're going to show that in this case, there are no feasible circulation. In other words, a circulation for which the flow is between the upper bound and the lower bound. And we stop. There is no solution to the problem. Or if one or the other is non-empty, or both non-empty, then we're going to change the dual variables. In this case, we're going to keep the flow fixed, and we're going to change the dual variable. So we're going to add this delta to all the node numbers in x bar. The y's in x bar. We're going to add delta to their dual variables, and we're going to keep the node number for the set x the same. So we're just going to touch the nodes in x bar. We're going to increase the node number by delta. So this corresponds to a change of node numbers. Well, that's going to impact the values of this adjusted cost, adjusted unit cost. Okay, and therefore it's going to impact the Kilter number. And lastly, by changing these node numbers, we had the flow breakthrough failed. By changing the node number, it might open up some loops or cycles where we could change the flow. We can change the flow from X star to Y star. Okay, so this is the node change process. So what you're going to have to do is, first I'm going to go through this. If A1 is empty and A2 is empty, then the problem is feasible. So we have to prove that. And two, if both of them are not empty, if either one is non-empty or both are non-empty, then this change we made to the node numbers did not impact. I should say this differently. This node change did not increase the Kilter numbers. Remember, the most important thing in this algorithm is that the Kilter number remain the same or decrease. They not. Okay, so let's prove infeasibility. When A1 and A2 are both empty, then the problem is infeasible. So what does it mean A1 empty? Remember, the definition of A1 is AXY greater than 0, and the flow is less or equal to the upper bound. So if it's empty, that means any arc from X to X bar for which the adjusted unit cost is bigger than 0, then f of xy has to be bigger than the upper bound. And of course, from the flow change rule, we know that if axy is less or equal to 0, then f of xy must be greater or equal to ub. Okay, because the flow change rule, let's go back to the flow change rule. So here we want to increase the flow, right, from x to x bar. So a of the adjusted cost is less or equal to 0, and f is less than ub. And in that case, we can label the destination of the arc, but that one failed because the flow change operation failed. That means that when A is less or equal to 0, F must have been greater or equal to the upper bound. Okay, so in any case, the sum of the flows between x and x bar is greater or equal to the sum of the maximum capacities of those arcs. Now, in the case where our original arc, we are decreasing the flow, F must have been bigger than UB. If A of x star y star is positive, then F is bigger than UB, just like here. Okay. Otherwise, if A of x star y star is less or equal to 0, then we go back to this is our the matrix, right? We are decreasing the flow between x and y. So the only case is this. We have three cases, right? This case, and this case. Our arc x star y star is not in Kilter, so it's not in these three cases. So these two, the flow is bigger than UB. Okay. In this case, the flow is bigger than UB. And then A positive, we already talked about that. So we go back to our the proof. If we are decreasing the flow from x star to y star, the flow must have been greater than the upper bound. So if we sum the flows from x to x bar, will be greater or equal to UB of x star. But in the case we are decreasing the flow, that inequality becomes strict. Now, how about the set A2? The set A2 also is empty. Then same thing here, just the opposite. AXY positive, AYX negative implies f of yx strictly less than the lower bound of yx. And A of yx greater or equal to 0 implies f of yx less or equal to the lower bound. And in this case, if we are increasing the flow from x star to y star, then the flow becomes strictly less than the lower bound. And here too, the sum of the flows from x bar to x is less or equal to the sum of the lower bound. And if it's an increase, then this inequality becomes strict inequality. Okay, now we are ready to prove that the problem is infeasible. First of all, F is a circulation. Remember, we always keep F as a circulation. So the flow from x to x bar must equal to the flow coming back from x bar to x. So this relation holds 0 equal to this holds for any circulation F. Okay, and from here, F is greater or equal to the upper bound, and this is less or equal to the lower bound. So we have also this greater or equal, but at least one of these two is a strict inequality. Either we are decreasing the flow on x star y star, or we are increasing the flow. So we have this relationship. And now from this relationship, the sum of the maximum capacity of the arc from x to x bar is strictly less than the lower bound of the arc from x bar to x. And that doesn't make sense, right? Because of this relation. The maximum flow that I can send from x to x bar is smaller than the minimum flow that I could send from x bar to x. That doesn't make sense, right? So there are no feasible circulation. Well, to prove it formally, let's assume that the problem has a feasible circulation. Let's call it f prime. Then we're going to have 0 equal to f prime of x bar minus f prime of x bar x. And if it's feasible, the flow should be less or equal to the upper bound, and the reverse arc should be greater or equal to the lower bound. So we will have this relation, but here will be less or equal to. Okay, and then we get UB of x bar greater or equal to the lower bound of x bar x, and that contradicts this statement here. So the problem has no feasible circulation. So now we entered the node number change, okay, and we made some modification to the node number. So that's going to impact the state of the arcs and, of course, their Kilter number. So we want to make sure that all arcs Kilter number did not increase. That's very important to the proof of convergence. So when did we enter this node number change? We entered this node number change when we had an arc x star y star, and we tried to put this arc in Kilter, and we went through the flow change process, and the flow change process failed, so there was no flow breakthrough. So we exited that process with a set of x of labeled node and a set of x bar unlabeled nodes, right? And then we formed the set A1 and the set A2, and you computed this delta. Remember, this delta was the minimum of the A's in A1 and A2. And then we added delta to the node number in X bar. And the node number in X remained the same. Okay, so that's going to impact the Kilter number of some arcs. And so there are many cases, right? There are arcs within X. In other words, the origin is in X, the destination is in X. Since the node number in X didn't change, then the A prime, the new adjusted unit cost, is the same. And the flow is the same. So that type of arc, the state would remain the same, therefore the Kilter number is the same. And the same with X bar. The origin in X bar, the destination in X bar. And both the origin and the destination, we increase the node number by delta. So those cancel out in the formula for the adjusted unit cost. So for those type of arcs, A prime will equal to A. And therefore, the state of that arc is the same and the Kilter number is the same. So now the only arc we have to worry about now is arc going from X to X bar, arc going from X bar to X. And of course, we have to worry about our original arc X star, Y star that we are trying to put in Kilter. Now, let's deal with the case first other than X star, Y star. So here we have an arc XY, X in labeled, Y unlabeled. So here we could not label Y from X. So therefore, we're going to eliminate this XY has to be in this 1-9 state. So we're going to eliminate we're going to eliminate 3 states. Remember, this arc goes from X to X bar. And in the labeling procedure, we want to increase the flow here. So therefore, this rules out this state, because if my arc XY is in state, I would have been able to increase the flow and therefore label Y. So my arc is not in this state, is not in this state, and it's not in this state. Now, also note that also in this state, if F was strictly less than UB, I would have been able to label Y from X, but I couldn't. Therefore, F must have been equal to UB. Okay, that's a remark here. That's going to be important in here. So let's look at every case and then see what happens. Let's look at before and after, right? So we have before, we have A positive and F is equal to the lower bound. And the Kilter number was 0. Now, F being equal to the lower bound, and the lower bound is less or equal to the upper bound, then F is less or equal to the upper bound. So we have A positive and F less or equal to the upper bound. That's exactly the definition of A1, right? And remember, the delta was the min of the A's. So the new A prime can only be greater or equal to 0. And therefore, so the A prime could be either positive or 0. So if it stays positive, A prime, then the Kilter number is 0. So we went from 0 to 0, no change. And if A prime is 0, then and the flow is between the lower bound and upper bound, right? From here is equal to the lower bound, so it's between the two. The Kilter number is 0 also, so the Kilter number did not change. How about A negative and the flow is equal to the upper bound? Well, A negative means A prime is negative. So the state before and after is the same, and the Kilter number is the same. So no change there. How about A equal to 0 and the flow is between the lower bound and the upper bound. Well, A equal to 0 means that A prime is negative, all right? But F is equal to the upper bound, all right? So I jump from this state to this state. And so the Kilter number, I jump from a Kilter number to 0 to 0. So there is no change in the Kilter number for this, for arc of this type. Now this one is, it cannot happen because Y was not labeled. So let's take this arc, A negative and F bigger than UB. And the Kilter number is F minus UB. So A negative, and we subtract delta, it stays negative. A prime is negative, and the flow is bigger than UB. So the Kilter number is F minus UB is the same. It didn't change. How about A equal to 0 and F is bigger than UB? Well, if A is 0, A prime is negative. So I jump from this state to this state, and both of them have F minus UB. There's no change in the Kilter number. So how about this case here? So A positive and F bigger than LB. Well, there are two cases in this. F is either less or equal to UB or F bigger than UB. If F is less or equal to UB and A is positive, that means this arc belongs to A1. And if it belongs to A1, A prime has to be greater or equal to 0. So you go with A prime greater or equal to 0 and F between LB and UB. So if A prime is strictly positive and F bigger than LB, then the new Kilter number will be A prime times F minus LB. But A prime is less than A. All right? So the Kilter number decreases. And if it goes to 0, right, A equal to 0, and F bigger than LB and F less or equal to UB, then I jump to this state, right? And my Kilter number is 0. So I go from a positive Kilter number to 0. So that's a decrease. Now, if F is bigger than UB, so A positive and F is bigger than UB, right? So in this case, the A prime can be positive, equal to 0, or negative. So if it stays positive, A prime is positive and F bigger than LB, then the new Kilter number will be A prime times F minus LB. But A prime is less than A. Therefore, the Kilter number decreases in that case. If A prime is equal to 0 and F is bigger than UB, so I go to this case, A prime equal to 0 and F bigger than LB, then the Kilter number there is F minus UB, right? But F minus UB is less or equal to F minus LB, which is itself less than A times F minus LB. So here I see a decrease in the Kilter number. Okay. And then if A is negative, if A prime is negative, and F is bigger than UB, then I jump to this case, A prime negative and F bigger than UB, then the Kilter number, the new Kilter number is F minus UB, equal to the, not equal, but F minus UB will be less or equal to F minus LB, which is itself less or equal to A times F minus LB. So I see a decrease in that case. So in any case, for X in X and Y in X bar, other than this X star, Y star, I showed that the Kilter number do not increase, and some of them will decrease. Okay, so let's now discuss the X star, Y star. Right? And when X star is labeled, that's the case. So for this, either X star is labeled or Y star is labeled. So let's do the X star label. So when X star, when the original is labeled, that means we want to decrease the flow on this arc. That's how we did the labeling process. So that this arc X star, Y star cannot be in this state. This, or this, because here we cannot decrease the flow here. We're going to make the Kilter number worse. So obviously X star, Y star is not in these three states. And so and also it's not in these three states also, because remember, X star, Y star is out of Kilter arc, and it's still out of kilter, so it cannot be in this state. So the only state that x star, y star, when x star is labeled, is these three: 1, 2, and 3. And the logic is the same as I did before for this arc. So in any case, the Kilter number for such arc from x to x bar, and also x star, y star when x star is labeled, did not increase, and some of them decreased. So now so we're going to do the other case. We're going to do x bar to x, and x star, y star when y star is labeled. Now we have to look at the other arcs from x bar to x, right? Yx. So the origin is unlabeled, and the destination is labeled. And of course, a prime of yx is equal to a of yx plus delta, because we increased the node number at y by delta. So this is, before it was minus, now it's plus. And also the case where x star, our original arc x star, y star, when y star is labeled. In other words, we started at y star and we tried to find a path to x star. And this case corresponds to when we wanted to increase the flow from x star to y star. So this is the case similar to the previous case. Now, I'm not going to go through it in detail. This is just a mirror image of the previous slide. So for one thing, for example, if we look to these arcs, yx, okay, remember that this is a reverse arc in our path. So we wanted to decrease the flow, right? And obviously, for example, in this state, a negative f bigger than upper bound, I would have been able to decrease the flow, but I couldn't. The flow change process failed. That means I could not label y. So that's why it's blue. So my yx arc is not in this state, or this state. And also here, it's similar to the previous one. F is not bigger. If f was bigger than the lower bound, I would have been able to decrease the flow and therefore label y. So here also, f has to be equal to the lower bound. Okay, and then the rest is similar. In case of f, before we had a1 here. Now in this case we have a bar negative, and f is equal to ub, which is greater or equal to lb, and therefore this arc belongs to a2, right? And similar, everything is similar, and it's just like I said many times, it's a mirror image of the other one. I'm going to skip the details of this. Now, so now let's so we went through. So we had a no breakthrough, right? We couldn't do any more flow change, and then we went through the node number change. We could have gone once, and we went back to the flow change process. We don't have a breakthrough, and we went another time. So what happened in that case? So the first time we went through the node change process, we had an X labeled node and labeled node. We formed the set A1, the set A2, and then we went a second time without any change to the flow. So we got another set X prime and its complement X bar prime, and we got a new set A1 prime and A2 prime. So now X is contained in X prime. Why is that? Because remember that within X, the A is equal to A prime, because the node number in X did not change. So whatever we labeled by the flow process, it's going to remain labeled. So X has to be within X prime, and and the flow remains the same. So we didn't change the flow. So X is inside X prime. So now there are two cases, okay? Either X prime is bigger than X, so it contained one more arc, all right? And then we do the same thing. We go back and do the same thing, and it keeps increasing. But x is contained is in a finite set. So x prime cannot be infinitely many times bigger than x. So at some point, x has to be equal to x prime. Okay. Then we have the following. So what is a1 prime by definition? a1 prime is the set of xy. X is labeled, y is is not labeled. That's x prime here, which is equal to x, by the way. And a prime is equal to a minus delta positive. Remember, a prime positive, and f is less or equal to ub. Well, if a prime is positive, then a is positive, because delta is positive, right? So therefore, this arc here that belongs to a1 prime, also belongs to a1. So this set is contained in a1. Same thing with a prime 2. A prime 2 is yx, y unlabeled, x labeled, and a prime becomes a plus delta. So if this number a plus delta is negative and f is greater or equal to lb, that's by definition yx belongs to a2 prime. But if a plus delta is negative, a is negative, because a will be less than minus delta, a negative. So this yx also belongs to a2. So therefore, these two sets, this set is contained in this set. Now, when we do the flow change, when we do the node number change, remember, we calculate this delta, right? One of the inclusion here is strict, because the delta is minimum of the a's in a1 and the minimum of the a's in a2. So one of them is the minimum, and for that, this a becomes 0. So this arc no longer belongs to a1. I'm sorry, it doesn't belong to a1 prime. So a1 prime will be strictly contained in a1. And if the minimum occurs in a2, then the a is negative when we add delta and it becomes 0, then this arc does not belong to a2. So every time, if x is equal to x prime, then we're taking one arc off a1 or off a2. And then the next iteration will take one arc of a1 prime or one arc of a2 prime. And of course, these are finite sets, so this cannot go on forever. So the rule, either x increases, right, in size, and that has to stop after finite number of iteration, or a1 or a2 decreases, and that cannot go on forever neither. So the conclusion is, with no flow breakthrough, the number of node change iteration is finite. Okay, so we showed that the flow change process cannot go indefinitely, and the node number change process also cannot go on indefinitely. So therefore, the out of Kilter algorithm converges in a finite number of iterations, provided that the input data is integer. Okay. So conclusion. This is the overall conclusion, the key points. So first of all, we have an integer input, both the lower bound, the upper bound, the unit cost, and the initial circulation, and the initial node number. All those are integers. Now, all the operations that we have discussed on the flow of the node number are of integer type. Okay. And the important thing is that the Kilter number are also integers and are non-increasing integer throughout. And for every successful flow breakthrough, one or more Kilter number decreases. And that's why we cannot go through the flow change process in infinite iterations. So therefore, the number of flow breakthroughs is finite. And then with no more flow breakthroughs, That's it. We could not change the flow at all. Then the node number changes is finite also, and that's why this this algorithm, the out of kilter algorithm, either produces the optimal solution, the optimal flow, and also the optimal dual variables, which, by the way, can be used to do sensitivity analysis on the final cost. We could use those numbers to figure out how can we even decrease further the total cost. So the out of kilter algorithm converges in a finite number of elementary operations. So that's the end of this the proof for convergence. Now next I'm gonna show an actual visualization of the out of kilter algorithm, and to go step by step and see exactly what's being done in the algorithm.
In this Excel session, I have a specific network that we will use to show the measure step of the Kilter algorithm and to provide the visualization of these steps. So the important detail of the algorithm will be pointed out. So I'm going to click on this, and here's the network that I selected. I have two cases depending on the input and these numbers. So I have one sheet that I called optimal, where I define these numbers. In this case, the Kilter algorithm find an optimal solution. And then I also have another case, which is I call infeasible, is another set of input data where the Kilter algorithm comes up and says there is no feasible circulations. And actually, it will provide the proof that such feasible circulation doesn't exist. So let's do this, the optimal case. And then I have here a step-by-step entry. Either I show step-by-step what the algorithm does, visualize what it does, or I say no, then the program will run in the background and it just come at the end and says, here's the solution. So I'm going to choose a no. So I'm going to click OK. And then it comes back. It solves this problem, and it's telling me that an optimal solution found. So in this case, I have added two numbers in the display here. One is the fourth number here, 6. That's the flow that goes, for example, here from 9 to 4. So that's the flow, 6, of the optimal solution. And the last number here, 0, is the Kilter number that we define when we when we discuss the Kilter algorithm. So for the optimal solution, all the Kilter number must be zeros. And here you see they are all zeros. So indeed, this is an optimal solution. Now, first of all, you could see clearly that this is a circulation. For example, here I have 6 flow coming in and 3 and 3. So the flow coming in equal the flow going out. And also, the flow is between the lower bound and the upper bound. And to be optimal, it has to satisfy the optimality conditions. And that we have to add node numbers, like you see here. And these node numbers are the values for the dual variables. Okay. And the optimal conditions state that, first of all, we have to compute the third number, which we call the adjusted unit cost. And it's equal to the unit cost minus the node number at the origin plus the node number at the destination. So that's called the adjusted unit cost. And the optimality condition says that when this number is positive, the flow must equal to the lower bound. And indeed, in my case here, 6 is equal to 6. And when the adjusted cost is negative, like in this case, then the flow, which is 21 in this case, it's equal to the upper bound. And indeed, here it does that. And when the flow is 0, like in this case, the flow has to be between the lower bound and the upper bound. So here it's 5, certainly between 4 and 10. So, and it satisfies, this is satisfied at all the arcs. So not only we have the optimal feasible solution, the flow, but also we have the optimal dual variables, which is the node numbers. So let's restart this algorithm, and then here I'm going to say yes. I want to visualize all the steps that this algorithm did to arrive at that optimal solution. So I start the algorithm. So now it has read the data from this sheet, which I called optimal, and then that first step is to initialize the algorithm. First, to initialize the algorithm, we need a starting circulation, not necessarily feasible circulation, but any circulation. And the easiest circulation to start with is 0. So 0 coming in, 0 going out. So it certainly satisfies the flow conservation equation. So that's the first thing. And then we also have to choose starting node numbers, as you see here. For example, node number for this node is 4, and so forth. And remember that the dual does not have any constraints. So here we could start with any set of node numbers. So here I started with this number. I could have started with 0 if I wanted to. And next, the initialization, we compute the adjusted unit cost, this number here, which is equal to the unit cost minus the node number at the origin plus the node number at the destination. Okay. And once we do that, then we calculate also what we call the Kilter number, right? And there are many cases for the Kilter number, right? For example, for this one, the adjusted unit cost is positive, so the flow must equal to the lower bound. But here the flow is 0, so it's not equal to the lower bound. So here the Kilter number measures the infeasibility of the flow, which is 6. That's why here it's 6. I have to increase the flow by 6 on this side for the flow to be feasible first. Another case, for example, here, the adjusted cost is negative, so the flow must equal to the upper bound, 20. So we have a 20 of infeasibility. Not infeasibility, but it's infeasibility plus not satisfying the optimality condition, 20. But also here, I have a choice also by changing the node numbers to make this minus 10 to be 0. If I am able to do that, then I only need to increase the flow by 2. So to measure both, we multiply 10 by the flow infeasibility, which was 20. So 10 times 20 is 200. Because I have a choice here. I have a choice to changing the node number or increasing the flow. Okay. In any case, we have to increase the flow by 2. And if we are able to change this to 0, I stop there. I don't need to increase it to 20. So we compute all of these Kilter numbers, and that's how the algorithm starts. And the objective now is so any arc whose Kilter number is not 0, so it's an out of Kilter arc. So basically, on my case, all of them are out of Kilter except this one that's in Kilter. Why it's in Kilter? Because the adjusted unit cost is positive, so the flow must be equal to the lower bound. My flow is 0 and lower bound is 0. And that's why this arc is in kilter. Now, so what the algorithm does now is to pick a out of kilter arc and then try to put it in kilter. Now, before we do that, this arc is in kilter, so this arc will always stays in kilter. The kilter number never increases. Whatever we do, we never increase the kilter number. So we either keep them the same or decrease them. So here, that doesn't mean that we are stuck with the 0 flow. I could change this to 0, for example, by changing the node number, and then increase the flow all the way to 10. I could do that. But that still makes this arc in kilter, so this number will not change. So the first step, it's going to choose an arc that's not in kilter, and it's going to choose 1 and 2 because it's the first on the list. So I do OK, and this is the arc that it chose, right? So the adjusted cost is 4, and my flow is 0. It's less than 3, so my kilter number is 3. So the first step in the algorithm is to try to increase the flow. So this is I want to increase the flow from 1 to 2. So I need to find a path, a round path, so that I could increase the flow in that loop. Okay, and it's going to start from this node. It's going to label this node, and it's going to label all the other nodes that it can. And then it goes to the other labeled node and try to label all the unlabeled node it can until we reach this node 1. And here we were successful. The argument was successful. It found a path here. And it's telling me I can change the flow by 2. Why 2? We needed 3 because this arc here, it's positive and the flow is 0. So positive means that the flow must be equal to the lower bound. So that's why I could only increase the flow by 2. So once we do that, this arc becomes in kilter, right? So we were working with this arc, but in the process, we made other arcs in kilter. So that's possible. So now I'm going to say, okay, go change the flow by 2. So it updated the flow, and look to this arc now, it's black, meaning it's in kilter. And we still have 1, right? Kilter number is 1. We are not done with this arc. So I continue. And in the same way, it found a path, this, where we could increase the flow by 1. And once we put the flow by 1, this arc becomes in kilter. So I do OK. And now it's black. So now it goes to the next arc that's not in kilter, which is 1 and 5. So here also it's positive, flow is 0. I need to increase the flow by 7. So it's going to find a path. And it says here it found a loop for flow change of 2. Right, I need 7, but I could only find a 2 because of this arc here. Right. The flow is 3. This is positive. I need the flow to be equal to 5. So I can only increase the flow by 2 in here. That's why it cannot go all the way to 7. So we're going to change that. So by the way, this one, once I add the flow of 2, this arc becomes in kilter. And the same thing, this arc also becomes in kilter. The flow is 3. If I add 2, it's going to be 5. It becomes in kilter. So I say, okay. And you see that these 2 are in kilter, but my starting out of kilter arc is still not in kilter. I need 5 more. So now I continue that, and now it's telling me the flow change procedure failed. Okay, I could not find a path from 5 to 1 where I could decrease the flow, and it has the labeled node. Remember that it starts with this node and try to label all the nodes it can, and then from here we start to label all the nodes we can, but we were unable to reach node 3 and node 1. So now we go to the node change, the node number change. We're going to change these numbers. And how do we do that? We look at the cut, the arc between the labeled nodes and the unlabeled nodes. So here I have 1, 2, 3, 4, 5. 5 arcs. And we're going to define those sets that I called A1 and A2. What's the set A1? A1 is the arc going from the labeled nodes to the unlabeled node. So in my case, there's only one of them here. So I look to the adjusted unit cost, and when it's positive and the flow is less than the maximum capacity, then I say, yeah, I can change the flow by 3 with just respect to A1. If I do that, I'm going to subtract 3 from here, and it's going to make this 0, and therefore I could increase the flow from 5 to 21 if I want to. But before I do that, I look to the set A2 also. And the set A2, I look for an adjusted cost negative, like this one. And I need the flow to be greater or equal to the lower bound, which is not the case here. So the set A2 is empty. So I only have A1 that's not empty. So here we're going to change the flow. We're going to change this number, the arcs. We're going to subtract 3 from the unlabeled nodes. So this becomes 4, and this becomes minus 8. And the labeled node will remain the same. So here I do OK. And look here, the adjusted unit cost is 0. That means now I could add flow on this arc up to 21, from 5 to 21 if I want to. So I need, it's telling me I need this loop here, I could change the flow by 4. Okay? So I go on, I change the flow by 4. And the arc is still not in Kilter. I still need 1 unit. Okay? So now I continue. And the flow change procedure failed again. But now I have 3 unlabeled nodes, and the rest is labeled. So the arc between the labeled node and the unlabeled node are this: 1, 2, 3, 4, 5, 6. Okay. Now we look to the A1 set, which is arc from the labeled node to unlabeled node, and here is just these 2. The other arc are going the other way. And then we look to the positive unit cost. I have 2 of them. And I look to the flow. Is it less than the maximum for this arc? Yes. And for this arc, yes. So then I take the minimum of the 2, minimum of 16 and 17. So the minimum is 16. Now also I look to the A2 sets. The A2 sets, I look for a negative adjusted cost. So I have only this one. And then I look to the flow. Is it greater than the minimum? Well, in this case, no. So A2 is empty. So the minimum is 16. So what I'm going to do then is subtract 16 from the unlabeled node. So this will become minus 6, and this will become minus 12 and minus 24. And in the process, by doing that, this number 16 becomes 0. And guess what? The flow, who was 5, who was stuck at 5, because this becomes 0, I could increase it all the way to 10. So I said yes. Updated the node number, and you see now this arc now becomes in Kilter. And I found a flow of 1 because this arc becomes open. So here we're going to change the flow, add flow of 1. And when we do that, this arc becomes in Kilter. We have selected, the algorithm selected this out of Kilter arc, right, and try to find a path to increase the flow from 0 to 4. So here he's telling me I can do that on this path here by 3 units. But notice here that, remember, we start from here and try to find a loop to this. But look at this arc here. It's going the wrong way, right? And then this one going the right way and reaching the origin 5. But what it means here is that the arc in the loop, the arc going the opposite way, we subtract the flow change of 3. So this becomes 0. And then we add it to this becomes 6, and this becomes 5. And then we add it to this one. So in a loop, it's not necessarily that all the arc are going the same direction. Some of them will be the right direction, some of them will be the opposite directions. And when you subtract, let's say we subtract a unit from here, but add it to the same unit to this one, the flow conservation is still the same, right? You subtract here, but add it here. Same thing here. I'm subtracting here and adding here. So the overall flow is conserved. Okay, now I'm going to exit this program. We don't need to go through all the steps. We already saw the optimal solution, so I'm going to cancel this. And now I'm going to show you another case where the problem is infeasible. That is, there are no feasible circulations. And I don't need to see the step by step, so I'm just going to do this. So the algorithm is going to read now from this file for the input. So I start the algorithm, so it read the input, and then I say OK. And it's going to try to find the optimal solution. And here we go. So it came out, it say, problem is infeasible. And it tried the flow change, it couldn't, so we stuck with this labeled node and this unlabeled node. And then when it went to do the node changed, both sets were empty. So for example, the cut is this one. So we look to from the labeled to the unlabeled. From the labeled to there's only 3. It's only this one. But the adjust cut is negative. So A1 is empty. How about A2? A2 is the other arc. So we look for negative A1. None exists. So A2 is empty. So when A1 and A2 is empty, the algorithm comes out and says there are no feasible circulation. And actually, it provides you a proof of that. Why? Because remember, this is a circulation. So the flow going from the labeled node to the unlabeled node must equal the flow going from the unlabeled node to the labeled node, right? That's the flow conservation. If you add all the equation corresponding to this set, you're going to find that. Now you ask yourself, what is the maximum flow that I can send from the labeled node to the unlabeled node? Well, in my case, there is only one arc here going from the labeled node to this. So the maximum flow I could send is 20. That's the maximum. Now, if I look to the flow from the unlabeled node to the labeled node, so these are all this arc, 1, 2, 3, 4, 5, 6, sending flow to the labeled node. And what is the minimum of such a flow? Well, all we have to do is add these numbers, the minimum. So 3 plus 4, that's 7, 9, 13, 18, and 21. So this says that the minimum flow I can send from the labeled node to the unlabeled node is 21. And the same flow is less or equal to 20. So that's a contradiction. So this problem has no feasible circulation. And this is a proof of that.